Hello everyone, welcome to my group theory lecture. In this lecture, we continue to study basic number theory. We begin with the relatively prime numbers. So here's the definition. We say two integers a and b are relatively prime if their greatest common divisor, their GCD, is 1. So they don't have any common divisor other than 1. In that case, we say A and B are relatively prime. Okay, so here's the theorem, a very important theorem. The integers a and b are relatively prime if and only if 1 equals, okay, ma plus mb for some m and n, right? So this is right, familiar to the the previous the theorem we talked about, right? Okay, so in this case, this C, the greatest common divisor, is the greatest common divisor of A and B equals 1. So you know we can actually easily see that why this equation is satisfied. Okay, right. uh, what's particularly important about this statement, this theorem, is that a lot of the problems, okay, a lot of problems, regarding relatively prime numbers can be proved using this property, this theorem. Second statement is if A and B are relatively prime and A divides B times C, then A must divide C. And the next one is if B and A are relatively prime, uh, oh, right. I'm sorry, there's typo again. Okay, I gotta fix this. So what it is supposed to be is, if B and A are relatively prime, uh, and C and A are relatively prime, then yeah, this is it. Then B times C and A are also relatively prime. So that's what it was supposed to be. Okay, so sorry about that. Okay, right, yeah. So to make sure that were the case, right. So I'm actually getting to my lecture note. Right. So this is the theorem. If B and C are both relatively prime to A, then BC is also relatively prime to A. Okay, so yeah, got that right. Yeah. So sorry about the confusion. So again, this the last statement is supposed to be B and A. If B and A are relatively prime and C and A are relatively prime, then B times C is and A is are also relatively prime. Okay, so I'll fix this. Right. So these two, okay, these two, the proof of it. I think, or yeah, the three of them, right? I think that the proof of this theorem is also, the part of it, the problem set. Okay, I'll talk about it later. But yeah, so the proof is left for the readers as an exercise. So particularly in this case, the 23 properties, 23 can be proven, I believe, using the first statement. Okay, so now we are moving on to prime uh, that's weird. Okay, that's another typo, not the prime of numbers. Sorry about that. Also, uh, you know, this is supposed to be prime numbers, just the prime numbers. Okay, right, prime numbers. Okay, so here's the definition. A prime number, or shortly prime, right? Shortly A prime is an integer greater than 1 such that for any, the integer A, either P divides A or P and A are relatively prime. So I know that, that you are familiar with the notion of prime numbers, right? Okay, but this definition doesn't sound different from the definition of a prime number you know of. So what you remember as the definition of a prime number most likely is this, right? So a prime number is a number, right? Um, the which has like what the the only uh, the divisor one and itself, right? Again, prime number is a number that has one and itself as the only divisors. So that's the definition you remember, right? In fact, the right. So this definition implies the notion of a prime number you know. Okay, so to show you that, let me get to my notepad. Okay, so keep that definition in mind. I just, mentioned. Okay, suppose that P is a prime. Okay, suppose that P is a prime. Of course, in the sense, that uh, uh, by the definition, right? P is a prime by the definition, I just introduced. Okay, so in that sense, this P is a prime, and then what I want to show is that in fact it coincides with the notion of a prime number that you are very much familiar with. Okay, right. So suppose that P is a prime number, a prime in short, and P is written as A times B, okay? A times B, where A is greater than or equal to 1, less than P. Okay, so with this assumption, to give you a heads up, okay, to give you a heads up, what I am going to show is that, the I'll show you that this A has to be 1, so then the P is going to be B. So that leads to the notion of a prime number that you are familiar with, right? Okay. So that's where we are heading at. Okay. Now, with this assumption, that since A is less than P, okay, A is less than P, so of course, P cannot divide A, right? P cannot divide A since A is strictly less than P. Okay, so by the definition of it, the prime number in that case, remember, in our definition, uh, if P is a prime number for any given integer A, either P divides A or P and A are relatively prime. Since P does not divide A, so the P and A has to be relatively prime. Okay, so we have this. Well, this implies that also, that by another property here, right? So P divides, remember like earlier, the one of the properties, regarding two relatively prime numbers. So P, so P equals AB, P equals A times B. So which means that P divides A times B. And P and A are relatively prime, so in that case, P must divide B. Do you remember that property, right? So P must divide B, okay? Right, actually, if it helps, let me go back. Right, so here's the property here, right? So, A and B are relatively prime, and A divides B times C, then A must divide C, right? So that's the property I was talking about, okay? Right, so we got this, okay? Right, so this means, okay, I can continue my, you know, implication arrow. So this means since P divides B, oops, so this means P is less than or equal to B. Okay, P is less than or equal to B. On the other hand, you know, B divides P because P equals AB, right? P equals AB. So P is a multiple of B, so P must divide B, right? So this implies that, of course, that means B is less than or equal to P. By combining these two, so P must equal to B. Done. So we proved, right? And of course, in this case, A equals 1. Okay, so we just showed that. So we see that actually our definition, right, implies the notion of a prime number that you are familiar with. Okay, right. Okay, so here's a theorem. Regarding primes, we have the following theorems. So the first one, let us talk about this first one. Uh, first statement says if P is a prime and P divides the product of integers a1 times a2 and so on and so forth times a sub n, then P must divide, right, some ai. Okay, P must divide some ai. This can be proven easily using, the an induction. Okay, right, an induction. So, oh, so theorem is P is a prime. P is a prime, and P divides a1, a2, dot dot dot, a sub n, then P must divide ai, okay, for some I. So here's proof. If P divides a1, well, if P divides a1, then we are done. Okay, we are done. Okay. If not, since P is a prime number, right? So, the where for this a1, a sub 1, either P divides a sub 1 or relatively prime by the definition of a prime number. So since P does not, if P does not divide the a1, then they have to be, the relatively prime. Okay, so in this case, P and a sub 1 are relatively prime. Okay, so that means again, by the property I mentioned earlier, right? One of the properties regarding to relatively prime numbers. In the case, P divides product of these numbers, but P and A1 is relatively prime. So P, in the case P must divide it, right? So this can be regarded as what? Product of two integers, a1 times uh, the other integer, a2 all the way to a sub n, right? So now P must divide this number here, a2 dot 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 a sub n, okay? Right. So we can continue this process. Now, if so let me go actually one more step. So if P, in this case, P divides A2, then again, we're done. We found that A sub I, we are done. If not, then P, oh, If not, P and A2 are relatively prime. Okay, so this implies that P must divide A3 dot 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 A sub n. Okay, so continuing this process. I mean, this process must terminate at some point. Okay, must terminate at some point because we have only like what the product of a finitely many integers. Okay, so the process has to terminate. I mean, what if we don't find any? Okay, we don't find any. Then, well, in that case, the p then that contradicts to the assumption that p divides the a1 through a sub n, the product of these integers, right? So there has to be continuing this process, right? Continuing this process, we must find, okay, we must find, we find that, P divides, must divide a I. At least there is one I somewhere for some, the I greater than or equal to 1 and less than equal to n. Okay, so this will be the end of the proof. Okay, so yeah. Okay, so next theorem is if n is greater than 1, then either n is a prime number or the product of primes. Okay, product of primes. Okay, and next one, very important theorem. It is called the unique factorization theorem. Okay, so let me introduce you without proof. Actually, the proof of this theorem is not difficult. You can prove this again using an induction. So given n the greater than equal to 1, there is a unique way to write n in the following form. So in terms of it's actually prime factors. So p1 to the power a1, p2 to the power a2, dot dot dot, p sub k to the power a sub k, where the p1 through pk in this order are primes, and the exponents a1 through ak are all positive integers. Okay, right. Extremely important and useful theorem. Lastly, this is due to Euclid. There is an infinite number of prime numbers. Okay, this can be also proved. It's not difficult to prove it, but this can be proved using a contradiction. But we are not gonna talk about it here. Okay, just need to know that there are, in fact, infinitely many prime numbers. Okay, so this is it. More details of my discussion in this lecture can be found in my lecture note at the following address. Okay, so as usual, I made a hyperlink. So, all you have to do is to click on this address and it'll take you to my note site. I briefly showed you earlier, right? And also, if you are interested in visiting my main Blogger site, just click on this word Blogger, which is also a hyperlinked. This is the place where you can find my many other lecture notes on different subjects of mathematics and physics. One more thing, okay, so I also made uh, uh, a problem set, okay, for the, you know, uh, what we studied, about the Bayesian number theory, right? And that problem set is available at the following address. It's pretty long, but you don't have to worry about that. Again, it is hyperlinked, so all you have to do is to click on this address and it'll take you there. Okay. All right. Thank you very much for listening and watching to my lecture. Bye bye.